Welcome to the next installment in a series of GIS tutorials geared towards local officials on how to use FEMA base-level engineering datasets in GIS to support flood hazard mitigation decisions. This tutorial series was developed by the Water Institute of the Gulf in partnership with FEMA Region 6 through FEMA's Cooperating Technical Partners Program. In today's tutorial, you will learn how to manipulate BLE data outputs to develop freeboard grids at predetermined intervals. Today's tutorial will cover three primary topics. We'll identify a group of geoprocessing tools we can use to approximate water depth at a given freeboard constant. Then we'll link those geoprocessing tools together into an executable model. Finally, we'll modify our model settings so that the model we built can be easily executed using a dialog window. So what exactly is freeboard? There are several definitions depending on the application. According to FEMA, it is an additional amount of height above the base flood elevation used as a factor of safety. For example, 2 feet above the base flood, in determining the level at which a structure's lowest floor must be elevated or flood-proof to be in accordance with state or community floodplain management regulations. For the purpose of this tutorial and for general floodplain management, we'll define freeboard as a factor of safety that compensates for unknowns which result in flood heights greater than the height calculated for a selected size flood. Freeboard is usually expressed in feet above a flood level and is not required by NFIP standards. However, communities that adopt at least a 1-foot freeboard requirement will see significantly lower flood insurance rates. Let's contextualize freeboard in the dimension of GIS. Essentially, we need to develop a process that can expand the floodplain based on a specific freeboard value. To do this, we're going to need several geoprocessing tools. The first geoprocessing tool we need to leverage is called Nibble and is available as part of the Spatial Analyst toolbox. Functionally, the Nibble tool replaces selected cells of a raster with a value of their nearest neighbor. It can be used to remove holes or incorrect values in a raster by assigning them values from adjacent cells. Look at the 100-year water surface elevation raster shown in the right figure. To expand the water surface elevation extent, we need to assign values to no data cells to develop a continuous surface to evaluate against a digital elevation model. Essentially, we need to remove the holes from the surface shown in the figure. Those holes, cells shown in red here, are no data in the water surface elevation raster. These are the cells that the tool is going to be working against, assigning the value of the nearest neighbor based on Euclidean distance. The output of that operation looks like this. You can see that we now have a continuous raster surface that we can evaluate against a digital elevation model. The second geoprocessing tool we will be employing is the Plus tool, part of the Spatial Analyst toolbox. Plus adds, that is sums, the values of 2 rasters on a cell-by-cell basis. This tool allows the user to assign a constant value as one of the 2 input rasters. Practically speaking, we need to adjust the values of the continuous water surface elevation raster by a specific freeboard factor. Take, for example, the output of the Nibble geoprocessing tool shown to the right with its associated symbology. Notice the range goes between 0 and 14 feet. We need to adjust the value of this raster by adding a freeboard factor. Let's adjust it by 1 foot. We can do this by applying the plus tool with a constant value of 1 as an input and the nibbled surface as the other input. The output of that operation is shown to the right. Notice the range now goes between 1 and 15 feet. Now that we have a continuous freeboard adjusted water surface elevation raster, we can compare it against a digital elevation model by applying a map algebra function using the raster calculator geoprocessing tool located in the Spatial Analyst toolbox. The map algebra function we'll be using for this operation is a conditional statement. The con statement has 3 variables, an input conditional raster and 2 rasters the input is compared against. One that has values if the condition is true, one with values if the condition is false. If the in conditional raster or statement is evaluated as true, it receives the true raster value. If it is evaluated as false, it receives the false raster value. Excluding the false raster from the original statement results in no data values for cells that are evaluated as false. This point will be important later. In practical application, we want to use the conditional statement map algebra function to identify cells where the digital elevation model value is less than or equal to our freeboard water surface elevation value. and then assign cells that match that criteria with a value that results from subtracting the digital elevation model from the water surface elevation. This output, shown in the figure to the right, approximates water depth at the freeboard factor we specified. Let's discuss how we can automate this process using the model builder functionality in ArcGIS Pro. Parameters and outputs are shown to the left, and the model builder framework is detailed on the right. Our model has two raster inputs: the water surface elevation grid for our desired flood event, a primary input into our model, and the digital elevation model that covers our area of interest. Notice that the elevation raster doesn't get fed into the model until we evaluate it using the conditional statement we'll develop. Our model also has 4 string input parameters: a freeboard constant, which in our case will be a numeric value, the vertical units of our water surface elevation grid, which we'll use to name our outputs, a HUC8 identifier, which we'll also use in our output file names, and the annual exceedance probability of the water surface elevation raster we're using, which will also be included in the file name of our outputs. Our model has 3 raster outputs, 2 intermediate and 1 final. The first intermediate output, the filled water surface elevation raster, is what the Nibble geoprocessing tool produces. The second intermediate output is produced by application of the plus geoprocessing tool, where we add a desired freeboard constant to the filled water surface elevation raster. The true output of the model is the approximate water depth at our defined freeboard constant. We'll detail how to calculate this shortly. We are using 3 geoprocessing tools in our model. Let's dig into the variables for each tool and some syntax for naming. Nibble, used to fill holes in our water surface elevation raster, looks like this. The input raster is our water surface elevation raster that we've assigned as a selectable parameter. The output raster uses a combination of unchanging strings and strings that are dependent on what is input as the HUC8 and annual exceedance probability parameters. The input dependent strings are enclosed with percentage characters, so the model understands that this part of the file name is assigned based on user input. Importantly, we need to check the Nibble No Data Cells option below the output raster name so that the tool explicitly knows to fill in the holes of our water surface elevation raster. Let's detail the values of the plus geoprocessing tool instance. The first input is the filled water surface elevation raster, the product of the previous Nibble tool. The second input is the numeric freeboard constant parameter. Our output raster name is a combination of unchanging string values and all our parameter dependent strings. Remember to enclose the parameter strings and percentage characters so the model knows to execute this tool using those parameters as part of the file name. Our final geoprocessing tool is a raster calculator that applies a conditional map algebra statement. Here's what that statement looks like. It only has 2 variables, our digital elevation model and the freeboard output raster, which you should remember is the output of the plus geoprocessing tool that added a freeboard factor to our nibbled water surface elevation raster. The input conditional statement evaluates digital elevation model raster cells that are less than or equal to co-located freeboard output raster cells. Cells that fit this statement, that is, cells which are true, are assigned a value based on the second expression, elevation subtracted from freeboard. The output of this operation approximates depth. Notice that there is no false raster assigned in the conditional statement. Cells that aren't true will be assigned a value of no data by the map algebra expression. As with other raster outputs in our model, the output raster name is a combination of unchanging string values and all our parameter dependent strings. Please remember to enclose the parameter strings and percentage characters so the model knows to execute this tool using those parameters as part of the file name. If you fail to do this, your model will not execute properly. Our model dialog should look like the figure shown to the left on this slide, assuming we've assigned our string and input parameters correctly. Parameter elements are detailed with a superscript P in the model builder framework to the right. A best practice tip here is to assign parameters in the order you want them to appear in the dialog window. You can assign parameters by right-clicking on the model element in the framework and selecting Parameter. The parameter element in the dialog window is the parameter element in the dialog window. You can assign parameters by right-clicking on the model element in the framework and selecting Parameter. The name of each model builder element is reflected in the model dialog. You can change the name in the framework by double-clicking on the element and typing in the name you want. We can also use the model dialog to specify the environment settings we want to control. In this example, I have set a specific processing extent to limit the time the model takes to execute. And I've also set a mask for raster analysis so that it limits outputs to the watershed I have BLE data for. Today's tutorial covered 3 primary topics. We used a group of geoprocessing tools to approximate water depth at a given freeboard constant. We linked those geoprocessing tools together into an executable model, and we modified our model settings so that our freeboard process could be easily executed using a dialog box. Thanks for tuning in.